very strange. Excuse me. Excuse me. And okay. I was sure to have material of the exercise number 2. However, consider this just now, and I want to do with you some comment about the obtained aerodynamic matrix, and I would comment with you the meaning of such a matrix as a function of the frequency. And this is a very important issue for better understanding concepts like the Stroll number or reduced frequency, for example. And so today I want to consider again this formula.
Prof, non sta condividendo, scusi.
Yes. Problem? I want to share with you this formula again, and this formula is giving the I want to consider this with my comment again. This formula is actually giving the generalized force in frequency domain as a function of the state space variable. And in this case, the state space variable are here the plunge and the pitch. Okay, so consider this. Let me. Okay, we have two generalized force, lift and moment, aerodynamic moment in frequency domain, and here are expressed by a matrix as a function of the Fourier transform of plunge and pitch angle. Okay, and here we have a 4x4, excuse me, 2x2 matrix dimensional, which has 1, 2, 3, 4 terms. We could call this term like E, L, H, E, L alpha, E, M, H, and E, M alpha. And what do these elements are? What do these elements represent? This is an overall frequency-dependent matrix giving us this vector, which is the vector of Fourier transform of the lift. This L tilde is the Fourier transform of the lift time function. And again, M tilde is the Fourier transform of the moment, the aerodynamic moment. And this is the output of this matrix. And in input, you have here the plunge, H tilde, which is again Fourier transform of the heave degree of freedom as a function of time, and finally pitch. Okay. Now, what is the meaning of this complex function here? And if you want to, for example, collect this term here, you have to find here all the coefficient multiplying H. So you have this, And here you have to collect all the coefficient multiplying alpha, for example, and these are this here, this, and this. And again, you can identify the other term of this matrix analytically. Remember that here we have the Theodosian solution, so we have an analytical solution. So this green term is the term giving the moment as contribution arising by H, the plunge. So we have this term here. And the last term, the yellow one, is given by this term. The other, this and this. Okay. So, what is the meaning of a frequency response function? When you have a frequency response function, an elementary frequency response function, here, in the elementary case, you have an H function of omega, applying to an input, giving you an output. This complex function in amplitude and phase is actually representing the time output of the input when you apply in time of the output, excuse me, when you apply in time an input elementary like sine omega t, and in output you should have again an harmonic response in harmonic steady state, in harmonic steady state. If you have this input, you should expect an output which is again a sine with the same frequency omega for a linear system, omega t, but as amplitude you have the amplitude of the complex number h evaluated in omega and a shift of phase given by the phase of the complex number h of omega. Okay, so this is the basic interpretation of any kind of frequency response function. And now you have, for example, here a term of this matrix like E L H term function of omega. What does it represent? The same. You have to expect, in the case you have an input given only by H, 0 alpha, and you want to see what happens to the lift, you have that the lift, the output, is an output given by this input multiplied by H L H omega, giving you L, exactly like here when you have Y and X as input. And so what does each term is representing? You have to imagine an elementary input for the heave. So imagine to have an heave like sine of omega t. So imagine to have an airfoil like this, and you have to move the airfoil with a sinusoidal motion like this, up and down, with the unitary amplitude, okay? So when you evaluate this complex quantity for omega to capital omega, you have a complex number, and this complex number is representing, in this case, the lift in steady harmonic motion. So the regime harmonic motion, harmonic steady state, as equal to the amplitude of E LH at omega fixed by sine of omega t plus the shift phase given by the phase of E LH. So this number for an assigned frequency is give you the lift generated by this harmonic motion plunge, which is again in a steady lift with an amplitude given by this number and a shift given by this number here. Okay, so we have an aerodynamic operator, which is mainly and namely a transfer function or a frequency response function for each term. So in this case, when you have as a state space variable, not the modal coordinate, but plunge and pitch in this analytic case, you may have this output whenever you imagine this kind of input. Okay? But we commented the issue, and you can see this issue just here, that this analytical model for the unsteady lift and moment, which is quite parallel to the numerical model we developed in the general theory, talking about panel method and the decomposition of this E matrix in E4, E3, E21, and so on. Okay, on commenting this aerodynamic, we concluded that we have a dependency of this matrix with respect to omega and U infinite as parameter. And you can see clearly here, this, you have U infinite here, you have U infinite here, and here as parameter. However, if you introduce the undimensional variable k equal to omega L divided by U infinite, you may include this dependency in only one parameter like k. Okay, and we could do this just modifying this expression and considering as undimensional frequency the reduced frequency like this. Now my point is the following. May I interpret this number, this k number? I have an interpretation of omega. Omega is the physical frequency of my unsteady phenomena. We can imagine an harmonic motion, as I did before, illustrating to you the meaning of E. And we know what is U infinite, what is a reference like L, for example. But what is K representing at the moment? So I would like to share with you a practical vision of this number. In order to do that, we have to imagine an harmonic motion, okay? And for example, in this figure here, I am imagining a pitching harmonic motion. Pitching harmonic motion means that I am considering this term here, for example. I am animating the pitch only, and so if I animate pitch only, I applied this vector to my matrix, and I will involve the term E alpha in this case for giving me L. So in this motion, we have L equal to H L alpha multiplied by alpha tilde, giving us L tilde as a complex number. And so if we activate an oscillatory motion like alpha equal to sine omega t, we should have in this case, for example, an oscillatory lift in steady state motion in time equal to, this case, amplitude of E L alpha evaluated at assigned omega by sine again omega t plus the phase angle of the complex number E L alpha. Okay. Okay. What happens physically when I impose a pitching harmonic motion like that? I should have any kind of quantity oscillating with the same frequency. Okay. And in particular, I will have an oscillation of any kind of quantity. For example, the vorticity shed by the leading edge here will oscillate as the airfoil is oscillating with the frequency omega. But pay attention, please. When the airfoil, can you see my arm here? Okay. When you have the oscillating of the airfoil, and this is the wake, we are going to generate here delta phi vorticity, gamma. In your basic aerodynamic course, you have gamma, and gamma is essentially delta phi, the jump of the velocity potential. But this delta phi is a steady quantity, and this steady quantity is shed on the wake, and then the wake, just like a tapis roulant, is able to transport this delta phi, as you know, downstream. Okay. So I have a mechanism of transport of the vorticity in the wake discontinuity, and a generation of this oscillating quantity by the airfoil moving with omega. Okay. Do you have in mind the old seismic meter for the earthquake? You have a pencil in a stick, and you have a paper in a roll, and you have this. You have a signal given by the amplitude of this pen moving up and down, and then you have a roll moving, and so you have a graph, okay, down. This is actually the same. So you have two parameters: the velocity of the paper, so the velocity of the speed, and you have the frequency of your mechanism. And what is the meaning of K? Well, if you consider this length, this reference length here, so the argument is meaning of K, which is defined like omega L by U infinite, okay? L is a reference length. For example, the chord means 2 times the half chord. We have used B as half chord, okay? And this is the chord at the moment, okay? So you have this length, and you have a time. Spent to cover the space L, and this time is T. So you have L equal to U infinite by T. Remember that the wake discontinuity is moving with velocity U infinite, with the relative velocity U infinite. And what about this T? This T is the time necessary for cover this space L by the wake shedding mechanism. And so this time T is equal to the period of oscillation, where the period of the oscillation is omega equal to 2 pi by capital T, and therefore the period is equal to 2 pi by omega. Omega is the frequency of oscillation of my airfoil. And so this period T is equal to, this time T, this time T is equal to the period T by N. And N is actually representing the number of cycles. N is the number of cycles that are present in a length L. Okay, so this N is equal to 2 pi, this T, is equal to 2 pi by omega, which is capital T, by N. And therefore, we have that kappa, which is omega comparing this with this, we have that kappa, which is omega L by u infinite, is equal to 2 pi n. This is the meaning of kappa. So kappa is a measure of how many cycles of disturbance on the wake are inside a length, apart the 2 pi factor. Okay, so in this case, in this figure here, you have here 1 equal one cycle. So if you count, you have an n number, which is something more 1, something less of 2, and so you have an n equal about 1.5, because you have 1.5 cycles in length, and therefore in this case k is equal to 1.5 by 2 pi, okay, which is something like 10 about, and therefore this situation here is a situation of a reduced frequency almost equal to 10, because you have 1.5 cycles in reference length. So the strong number is a measure of on about how many cycle generated by this harmonic source are present in a length on the wake, so including the mechanism of wake shedding, because we are assuming that this disturbance is conducted by the airfoil with a velocity equal to u infinite. Okay, so you have two possibilities for increasing this the number of this perturbation in length. You have only two means for doing that. You can increase the frequency omega, and if you increase the frequency of the pitching, you should have more and more wave inside this length, but you may also decrease the velocity, u infinite, of your tapis roulant for having more. In fact, you have a numerator and denominator with omega and u infinite as characters of your reduced frequency. And you are considering the ratio between these two leading phenomena for characterizing K. Okay? This is the essential parameter influencing the unsteady aerodynamic in the linear framework. Okay? It's not only in absolute frequency, but the driving phenomena is the frequency with respect to velocity of the speed, with respect to the velocity of the stream. Okay? Because the velocity of the stream is regulating the shedding, the wake shedding mechanism for regulating your unsteady aerodynamic. Okay, so this is important. This point is important. This interpretation, let me conclude and give you a final comment. So this is kappa, which is essentially related to n, which is the number of cycles that are present in a length L. And we have a comment on strategy for deciding the mesh panel in panel method. panel method is a space discretized form of this analytic theory, which is valid in 2D. If you consider a specific discretized approach for this, you will have the panel method, as we have demonstrated in the past lectures. Now, here I have the interpretation for K. And imagine to decide a strategy for discretizing this airfoil by dividing the airfoil in panel like this: panel, 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 panel. And also the wake. Divide the wake in panel, 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 panel. Okay. And in each panel of the wake, you should have a delta phi quantity here, and you have a phi on the body panel. So, do you have any kind of limitation on deciding the mesh of your paneling on the wake or not? If you imagine a frequency and an elementary frequency motion, and you know very well that a general motion is a superposition of frequency motion, okay? But so concentrate on an elementary harmonic motion. If you have an elementary harmonic motion, you have a harmonic, a wave trend of your quantity on the wake. And you should be able to represent this harmonic variation on the wake. So your mesh, your panel subdivision should allow to you to represent this harmonic representation. This is something very, very similar to the Shannon sampling theorem in telecommunications. You should be able, with your wake sampling, to represent an elementary harmonic. Okay, higher and higher is the frequency, more and more elements you should use in your wake discretization. This is easy to understand. And therefore, for example, the question could be, which is the minimum? Which is the minimum panel length of your discretization? This question is very easy. For example, if you decide, if this is L, this L is the length of one wave associated to a velocity and to a frequency. So whenever you fix omega and u infinite for a period capital T, you have a length. You have this length, and your paneling should be able to, your panel strategy should be able to describe your harmonic oscillation in a wave length lambda. And this means that for example, if you decide to suppose to describe your wave in lambda by 10 panel minimum, so 10 panel. This number is something like the number 2 for Shannon for Shannon theorem, you accept to have 2 points, minimum 2 points, for represent a wavelength in time in this case. So supposed to have 10, just to be more oversampling generous, okay, oversampling. If you decide 10, so your delta x of the panel should be less than your lambda minimum divided by 10. But lambda is equal to u infinite by u infinite by capital T divided 10, and this capital T again is 2 pi by omega. So you have u 2 pi by omega by 10, and so this omega is actually this omega here. So you have a minimum lambda, so you have a maximum omega. So your higher frequency of the airfoil motion is the worst case for you in terms of panel, okay? So you have lambda minimum, so you have omega max, and this omega max divided by 2 pi is your maximum frequency of your problem. So you have u infinite by f max, okay? And you have a 10. This 10 is representing your decision to represent this worst case minimum with a number of 10 panel for the higher frequency of your problem. So this final formula here, let me write this here, delta x less than divided by 10 means 0.1 u by maximum frequency is the thumb rule, is the magic formula for deciding the number of panels necessary for represent your aesthetic phenomena. If you have very low velocity is obliging to you to have a low value for delta x, and higher frequency, maximum frequency, is obliging you also to have a very, very small delta x. So when you are studying a steady aerodynamic and you have a wing, with a wake, the number of panels in, this is the y direction, and this is the x direction. The number of panels in the transversal direction like this is just dictated by the capability for describing your elastic deformation, so your mode, including the analysis, essentially. But the discretization in the flow direction, in the x direction, this here, and again in the wake, is affected by minimum velocity and maximum frequency because of this discussion on the Struel number on or reduced frequency. Okay, and therefore the space mesh of your phenomena is affected by the frequency you are interested on study. So the speediness of your phenomenon and the velocity. It looks like a paradox, but lower velocity of the flow obliged you to have higher and higher number of the panel in the X direction, in the flow direction. Okay? Okay. So this is a very important issue for a steady flow discretization in space. Now, and this is a first point of our discussion today, a first complementary point for you. I have another complementary point for you concerning our steady aerodynamic. This complementary point, we have a complementary point number 1, which is the meaning of K and related issues here. Now, next, we have complementary point number 2. And this point number 2 is, I promised to you to go in deep on domain function. Ex. We discussed it for we discussed it for commenting the boundary integral equation in the case of X in the belonging to the flow and X belonging to the body. So we have body, and we have here E is equal to 1, and here the X is equal to 0, and here E is equal to 1/2. This is a very interesting point, and remember that this X is in the reality an X star point. X star is the point we use for collocating our solution. Okay. So consider, for discussing this, consider an X star point here. And you are seeing by this point a piece of domain surface like this. This is S, and we want to see a point in the surface X here. Remember that we have in the formulation, we have phi in the X star point equal to the integral of blah 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 dx, ds of X. So X is a point on the surface. I am integrating on this surface, and X star is a fixed point. Okay. Now this is the surface S, and we have a portion here of our surface like this, a portion. And here I have my eye, a blue Spanish eye like this. This is my eye here in this point, and I'm seeing by this point, at this point I, this elementary surface, and this elementary surface is the elementary surface ds. And now I want to I'm seeing this elementary surface by my eye here, located here. So this surface has a normal. This is the case. I am inside the body, for example. Okay. And here I have a normal. And I have also a sphere with center in my X star point, and my sphere as a radius like r, and this is the surface of a sphere centered in this point. And beside ds, I have also the elementary surface on this sphere, like this. Okay, and look, we have a vector, and this is the x point. Excuse me, I forget to say to you, to remind you that this is my x point. So I have x and x star. Okay, and this distance is r equal by module of x star minus x vector. Okay, and so I have also, this is the amplitude of this vector, and I have also a vector like r, and this is the vector r vector, or simply underlined. My vector r is equal to vector position vector x minus position vector x star. Okay, standard. And I have also a unit vector in this direction. This unit vector, this here, is the unit vector ER, is a unit vector in the R direction. Okay. We have an angle between the normal, which is a unit vector as well, and the unit vector ER. And this angle is theta. This angle here, theta. Theta. Okay, so we are ready for example, we have two elementary surface. We have the area ds. Excuse me. We have the area ds. You see this area, this is a black area ds, and we have also the red area ds sphere. So we have ds p. dsp is the red one on the sphere, and we have an angle. You may imagine n as the normal to ds, and e theta er, which is normal to the elementary surface dp, and therefore we conclude that the elementary surface ds is equal to dp ds, excuse me, by the cosine of theta. Okay, because theta is the angle between the normal m and the unit vector er, and therefore theta is also the angle between the elementary surface dp and the vector ds. Okay, so we have something like that. We have dp, you have dp, and we have ds. Okay. This is theta. Okay. Now, what about ER? ER, unit vector, is equal to vector R divided by the amplitude of R, because this is the unit vector. We have that the cosine of theta is equal to n dot ER. And next, we have to define what is a solid angle. What is the elementary solid angle d omega by mean the point x star c the elementary surface. Yes? Question? This is a solid angle. A solid angle is a measure of the vision of this surface by this point in the space. Okay? The concept of solid angle is something similar to the concept of the measure of an angle in a plane in radian. When you have an angle in the plane, a standard angle in the plane, you have alpha. In order to quantify this alpha, what you do? You consider a circle with the center in alpha, and then you consider the circle here. You have an arc length of this circle, and you have a radius of this circle, and you decide that this alpha, the measure of alpha in radian, is equal to the ratio between L with respect to R. In the case you have a unit radius circle, you have essentially the length of this arc for measuring your angle alpha. And this is the same, but now here you have to take the ratio not of arc length with respect to the radius, but you have to compare surface. And in particular, here you have the L of a unitary circle with respect to 1. Okay? And what can you do parallelly for this concept? You consider a ratio between the area of the sphere with unit radius. This is, excuse me, you have to consider a sphere with unit radius here, 1, and you consider this ratio d omega, this arc length, divided to 1 to the power 2, which is 1, of course, just to be a parallel. So in this formula, you have that the angle in radian is essentially equal to the length of the circle with the unitary radius. Okay. Parallelly, you have to consider this proportion between your elementary surface with respect to 1, and you have to compare this with the DSP, the present elementary surface, not this in the circle, not this, but you have to consider this. So you have to consider not a generic surface, you have to consider the surface of the sphere with radius equal to R. So SP, not DS, DSP, divided by the square in proportion, the square of the sphere, of the sphere radius, excuse me. So this is the definition of the angle in radian. The angle in radian of the angle seen by a point which is seeing a surface S is essentially the projection of such black surface here onto the sphere with the center in the point and with the radius equal to 1. And this is the measure of the angle in radian. And we can obtain this by our draw here, just applying this proportion. The omega by the unitary radius to the power 2 is equal to dsp, not ds please, but dsp with respect to divided by the square of the radius of the distance between here and here. And so this dsp is equal to the cosine of theta by ds divided by r to the power 2, and the cosine is equal to n dot er. So we have that the elementary angle in radian is equal to cosine n dot er by ds divided by r to the power 2, but er is r divided by the modulus of r, and so this is equal to n dot r, the vector, ds divided by r, the amplitude, to the power 3. So we have an expression, an analytic expression of the angle in radiant, in steradiant. Oh, excuse me, I used the word radiant, but I want to say steradiant. This is radiant, and this is a steradiant. Okay, the omega. Okay. Now, the objective of this discussion is the following. We want to evaluate. I have to skip. No. I don't want to skip. I want to. This is the preliminary of this discussion. The elementary expression of the angle in steradiant. And now my objective is the following. I want to interpret this coefficient, which is CKM coefficient, which is evaluated by taking the integral of the derivative of n of the source, which is 1 on 4 pi r, okay, in ds. Remember, we use this coefficient for discussing the two metrics, and this was also called the doublet coefficient. Okay. I don't know if I have the old figure. Maybe yes, we have here. No, I don't have. However, it's not easy to. It's very easy to recap this point. When we 10:03. Okay, I stop here for a pause, and I will recap you this concept, and for finishing this discussion about the domain function Ex. Okay. Excuse me for this delay, and let's have a pause now. Thank you.